Jai Hind students, welcome to my YouTube channel. Students, I am very sure that you are studying real hard. You are concentrating on your studies and you are dedicating and devoting yourself completely towards your studies. Do remember students, study hard. No matter if it seems impossible, no matter if it takes time, no matter if you have to be up all the night. Just remember students, the feeling of success is the best thing in the entire world. So through your hard work, when you will achieve success, that I am sure will give you immense satisfaction. That will propel you to move and march forward. Right? So with that students, let's start today's session. In the previous lecture, we have discussed some terms and definitions. This lecture is in the extension of that lecture only. And in case you have missed out on that, in the description section of this present lecture, I will provide you the link of my previous lecture. Right? So today we are going to discuss these terms. Magnetic induction, then magnetic susceptibility, magnetic permeability, relative magnetic permeability, and then the relationship between magnetic susceptibility and relative magnetic permeability. So these are the topics which we will be covering in this particular episode. Right? So let's start with magnetic induction. Let us start with magnetic induction. Right? It is magnetic field strength. Right? So before we discuss the actual definition, just let me just introduce this topic. Right? What to do is, let us consider vacuum in which magnetic field B naught exists. And we are aware students, H, you must remember, it's the magnetic intensity. And in vacuum, this magnetic intensity is given by B naught divided by mu naught. So this B naught, which is the magnetic field which is assumed to be present in vacuum, it will be equal to mu naught H. Clear students? So what we have assumed is, this is magnetic field B naught in vacuum. So the magnetic intensity would be B naught divided by mu naught. Right? Now suppose in this vacuum where magnetic intensity H is there and magnetic field B naught is present, this is the external magnetic field. Suppose this magnetic specimen is placed under the influence of this external field. So this being magnetic specimen, it will definitely get magnetized. All the atomic dipoles inside the specimen will orient themselves in a common direction. So that one end of the specimen will act as the south pole, the other end of the specimen will act as the north pole. So students, this magnetic specimen under the influence of this external field will get magnetized. So this is known as magnetization by induction or simply magnetic induction. Right? So as the specimen gets magnetized, it will develop its own magnetic field lines. So in that case, in such a case, total number of magnetic field lines inside the material of the substance crossing normally per unit area of the specimen, that will give us the measure of the magnetic induction. Right? Well, I will draw the third diagram. I will come back to that definition once again. But before that, as the magnetic specimen is placed under the influence of this external field, what happens? It will get magnetized and it will develop its own magnetic field lines. Suppose, let's consider this to be a ferromagnetic substance. Later on we will discuss a ferromagnetic substance gets strongly magnetized along the direction of the external field. So that this will acquire, this end will acquire south polarity and this end will acquire north polarity. Right? It will get magnetized. So it will develop its own magnetic field lines, and the field lines will be directed inside the material of the body. It will be from south to north like this, and outside it will be from north to south in this manner. This will be the field lines due to this magnetization of this magnetic specimen. As we are aware, field lines are in the form of continuous closed loop. They don't have any starting point, neither they do have any terminating point. It should be like this. Outside the body of the magnet, it will be from north to south, and inside the body, it will be from south to north in this particular manner. Right? Now just imagine the field lines will get modified. So this will be the third diagram. And let us consider this to be region 1, this to be region 2, this to be region 3, and this to be region 4. I repeat, this region 1, this is region 2, this region 3 and region 4. Just imagine students, here the magnetic field due to this magnetic specimen is from right to left, while the external field is from left to right. That is, both are of opposing nature. So they will oppose each other, right? Here also the direction is opposite. The magnetic field line due to the magnetization of the specimen is directed from right to left, but external field is from left to right. So here in region 1 and 2, the magnetic field, net magnetic field strength will get deteriorated, isn't it? Due to the opposing nature of the magnetic field due to the specimen and the external magnetic field. While in the region 3rd and 4th, here, due to the magnetization of the specimen, the magnetic field lines are also directed from left to right. The external field is also directed from left to right. So, in the region 3 and 4, the magnetic field strength will get strengthened. It will get strengthened, isn't it? So, I will draw this diagram, the modified version, right? So, it will be like this. This will be south, this will be north. So, magnetic field lines will be like this. So magnetic field lines will get strengthened in the region 3 and 4. This is region 3 and this is region 4. While in this region, the field lines will get weakened. This is region 1 and this is considered to be region 2. So through the diagram, it's pretty clear that when a magnetic specimen is under the influence of external magnetic field, then the specimen gets magnetized. It develops its own magnetic field lines, isn't it? So in that case, suppose this is the 3D diagram. In such a case, total number of magnetic field lines inside the material of this specimen, inside the material of the substance that crosses normally, means perpendicularly, per unit area, per unit this cross-section area. That gives the measure of magnetic induction. It's nothing, students. Actually, in the previous lecture we have discussed magnetic flux and it is defined as BA in case theta is 0 degree. Theta was considered to be the angle between the magnetic field and the area vector, isn't it? Theta is the angle between the magnetic field and the area vector. So magnetic flux is defined as scalar product of magnetic field and area vector. In case all the magnetic field lines crosses normally, then flux is given by B into A. So here B is the magnetic induction and it is phi B divided by A. So just remember this mathematical form and this is the qualitative definition of magnetic induction. So flux, we are aware, it is the number of magnetic field lines crossing normally, isn't it? And per unit area, that gives the measure of magnetic induction. So again I repeat, students, magnetic induction may be defined as total number of magnetic field lines inside the material of the substance crossing per unit area normally, that is in the normal direction. And obviously the SI unit of magnetic induction is Tesla. It's normal magnetic field, isn't it? So let me write down the first definition, right? This is it. So it is defined as magnetic induction is defined as total magnetic field lines, inside the material of the substance, inside the material per unit area, crossing per unit area, inside the material crossing per unit area, and what direction? normally, that is perpendicularly. So this is one of the definition of magnetic induction, right? So total number of field lines inside the material of the specimen crossing per unit area normally through it, that gives the measure of the magnetic induction. You can remember this theoretical statement with the help of this mathematical expression. Clear, students? So students, now let's discuss the quantitative study of magnetic induction, right? Now as stated earlier, B naught is the magnetic field strength or magnetic induction in vacuum. It is due to the magnetizing field H, which is B naught by mu naught. Once this magnetic specimen is placed under the influence of this magnetic induction B naught in vacuum, then what happens? The specimen gets magnetized, isn't it? It develops its own magnetic field lines. So these are the magnetic field lines. Now, once this specimen gets magnetized, now the total number of magnetic field lines inside the material of this specimen crossing per unit area normally, that gives the measure of the magnetic induction inside the material. So this is the theoretical aspect. Now using this theoretical aspect, let's try to find out an expression for the magnetic induction, right? So magnetic induction inside the material would be given by, in the vector form, it would be given by the sum of the magnetic induction in its free space, which is considered to be B naught, and the magnetic induction, suppose Bn, caused by the magnetization of the material, right? So here I have written the magnetic induction developed in the material. This is the magnetic induction in the vacuum due to the magnetizing field H. Now magnetic induction is the net magnetic field lines inside the material crossing per unit area normally. So it involves both the magnetic induction in vacuum plus the magnetic induction due to its own magnetization. So definitely the magnetic induction developed in the material will be given by the sum of the magnetic induction in the free space, which is caused by the magnetizing field H, and the magnetic induction due to its own magnetization. So students, please, you need to note down this theoretical statement, right? Once again I am repeating. The magnetic induction developed in the material is the sum of the magnetic induction in the free space caused by the magnetic intensity H and the magnetic induction, say Bn, caused due to the magnetization of the material, right? So let us expand it. So B in magnitude, it would be equal to B naught. As we are aware, it's mu naught H, isn't it? Plus, we have discussed the intensity of magnetization, isn't it? I, intensity of magnetization. The extent to which a specimen gets magnetized, that's intensity of magnetization, which we have discussed in the previous lecture, right? So, Bm is the magnetic induction caused by the magnetization of this specimen. So, by definition, Bm must be equal to mu naught I. Here, I is the intensity of the magnetization, which gives the measure of the extent to which the specimen gets magnetized, right? Therefore, students, magnetic induction inside the material would be given by mu naught H plus I. So this is the relationship between magnetic induction, magnetizing field and the intensity of magnetization. Clear? So this is a very, very important relationship. And as you have discussed regarding the SI unit of magnetic induction, obviously its SI unit is Tesla, which is represented by capital T. Another unit is Gauss, and one Gauss is equal to 10 raised to the power minus 4 Tesla, right? So Gauss and Tesla are the units which we use to express magnetic induction. So this is the definition of magnetic induction developed inside the material. This is the magnetic induction in vacuum. And magnetic induction or magnetic field may also be defined as force per unit north pole placed at that point. Isn't it? That is another definition of magnetic induction, or simply magnetic field, or strength of magnetic field, or magnetic field intensity, all the same. So we are over with this topic, friends, magnetic induction. Now let's proceed to the next topic, which is very, very interesting one, and it is magnetic susceptibility. Next one is magnetic susceptibility. Do you know the literal meaning of susceptible? Susceptible, literal meaning of susceptible. Literal means dictionary meaning of susceptible. Susceptible means readiness or aptness, the quickness. So how readily a specimen gets magnetized under the influence of external field? That is susceptibility. So basically, susceptibility means it gives the measure of the aptness or the readiness of a specimen to get magnetized. There are some magnetic materials which get very, very easily magnetized, like soft iron, while there are some other magnetic substances which require long enough time to get magnetized, which are very difficult to get magnetized, right? So let's discuss magnetic susceptibility. It is denoted by chi. This is chi, CHI. Chi M, magnetic susceptibility. Right? We will denote it by chi N. You must remember electric susceptibility. There we represent it by chi E. That's electric susceptibility. So students, susceptibility, it gives the measure of the aptness or readiness of a magnetic specimen to get magnetized. Clear? So it is the physical quantity which gives the measure of the aptness or the readiness of a magnetic specimen to get magnetized. Those substances having high value of magnetic susceptibility means that they get magnetized very quickly, readily. Mathematically or quantitatively, magnetic susceptibility is defined as the ratio of the intensity of magnetization to the magnetic intensity. This is the mathematical definition. So I is the intensity of magnetization. It is the intensity of magnetization, while H is the magnetic intensity. So mathematically or quantitatively, magnetic susceptibility is defined as the ratio of the intensity of magnetization to the magnetic intensity. Now both are having unit of ampere per meter, isn't it? So therefore students, it is but obvious that chi, which is the magnetic susceptibility, being the ratio of two similar physical quantities, is a dimensionless quantity having no units. So it will have a no unit. It's a dimensionless quantity. Clear? So that's susceptibility. Okay. Next is students, magnetic permeability. Magnetic permeability. Permeable will denote it by mu. So basically, it gives the measure of the conducting power of a magnetic specimen towards the magnetic field lines. Means how it allows the magnetic field lines to pass through it. So that's magnetic permeability. Clear? So magnetic permeability is a physical quantity that gives the measure of the conducting power of a specimen towards the passage of magnetic field lines. So basically, it gives, magnetic permeability gives the measure of conducting power of a magnetic specimen towards the passage of magnetic field lines, towards the passage of magnetic field lines. So how much the magnetic specimen is allowing the field lines to pass through it, that is actually measured by magnetic permeability. So it actually denotes the conducting power for the passage of magnetic field lines through the material of the specimen, right? Now quantitatively or mathematically, this permeability is defined as the ratio of the magnetic induction to the magnetic intensity. So B stands for magnetic induction, just now we have discussed, to the magnetic intensity. Clear, students? So mathematically, magnetic permeability is defined as the ratio of the magnetic induction to the magnetic intensity. Now, regarding its unit, magnetic induction, its SI unit is Tesla. H, magnetic intensity, its SI unit is ampere per meter. So, the SI unit of mu would be Tesla meter per ampere. Clear, students? So, the SI unit of magnetic permeability is Tesla meter per ampere. Next is relative magnetic permeability. Relative means with respect to relative magnetic permeability. It is denoted by mu r. Just as was in electrostatics, we have discussed relative permittivity. Here we are discussing relative permeability. So basically it is defined as the ratio of magnetic permeability of the medium to the magnetic permeability of free space. So this is the definition of magnetic relative permeability. So the magnetic relative permeability of a substance is defined as the ratio of the magnetic permeability of the substance under consideration to the magnetic permeability of free space, that is vacuum. And we are aware of the value of mu naught. The magnetic permeability of free space or vacuum is 4 pi into 10 to the minus 7. It is Tesla meter per ampere. Isn't it? Now look, students, this is permeability of the substance, this is the permeability of the free space. Both are having same units, that is Tesla meter per ampere. So again, relative magnetic permeability being the ratio of two similar physical quantities is a dimensionless quantity with no unit at all. So I hope you have understood this concept, students. Again, I must repeat, susceptibility means it gives the measure of the readiness or the aptness of the specimen to get magnetized under the influence of external magnetic field, right? Permeability means it represents the conducting power of the magnetic specimen towards the passage of magnetic field lines. Relative magnetic permeability means ratio of the permeability of the material of the substance to the permeability of free space. So that is how we can define magnetic susceptibility, magnetic permeability and relative magnetic permeability. Now students, let's discuss the last topic, which is the relationship between the magnetic susceptibility and relative magnetic permeability. So that's a very, very important relationship. You must recall similar relationship between the dielectric constant or relative permittivity and electric susceptibility, isn't it? So same is here also. We will discuss the relationship between chi m and mu r. So let's discuss this particular topic. For this, we will make use of the mathematical expressions which we have discussed during these topics. So, let's find out the relation between magnetic susceptibility and relative magnetic permeability. Right? Okay. For this, we know that we will make use of all the topics which we have discussed in this session and in the previous lecture. So we know that the magnetic induction inside the material is given by just now we have discussed, B is equal to mu naught H plus I. You all are aware of this, isn't it? So H is the magnetic intensity, I is the intensity of magnetization. So we have to make use of this formula. Also students, if you divide throughout by H, what we get is dividing throughout by H, which is the magnetic intensity. What we get is B by H, it will be equal to mu naught H by H plus I by H. So what do we get? B by H is magnetic permeability. Just now we have discussed. H by H, it will be equal to 1. I by H, that is magnetic susceptibility. So here you can write it down. So mu, magnetic permeability, is B by H, and magnetic susceptibility is I by H, isn't it? Now, still further, mu by mu naught is equal to 1 plus chi n. And students, this is the relative magnetic permeability, which is the ratio of the magnetic permeability of the material of the substance to the magnetic permeability of free space. So this is mu r. It is 1 plus chi n. So please do remember this relationship between magnetic susceptibility and relative magnetic permeability. So mu r is equal to 1 plus chi n. So this is again a very, very important relationship. So we are over with this topic as well. So students, I hope now you must be confident in dealing with some other topics related to classification of magnetic materials. I am very sure now, as we will discuss some more topics related to the properties associated with diamagnetic, paramagnetic and ferromagnetic, you will be really, really convinced of whatever I will teach you, right? So that's it for this particular session, students. Do join me in my next lecture then. Have a blessed day and thank you.